To develop our intuition for how vorticity evolves in an ideal barotropic fluid, we're going to start considering the Kelvin circulation theorem. To get us started, we have our vorticity evolution equation. Our vorticity changes only by del cross u cross omega, which, as we saw before, is given by a shear stretching term and also by a compressibility term. And we've seen how to understand for simple flows how the vorticity changes due to by examining the math here. But now let's see how the vorticity changes via drawing pictures, which can help us understand more complicated flows. Let's start by considering our flow and consider some surface in our flow. We'll call this S1. And at our surface S1, there's vorticity in our flow. Here's our vorticity vector, omega. At that surface, there's also a flux, and the flux of vorticity is given by our omega vector dotted with our surface. All right. Now at some later time going this way, let's draw some new arbitrary surface in our flow, S2. And this also has a bunch of vorticity pointing through it, a flux of vorticity. And the surface S2 is the parcel S1 deformed and changed in time. So all of our vortex lines, they were in S1 and now they're in S2. And they're connected so that the lines through S1 continue through S2 as the fluid changes and deforms the surface. And here, again, our flux is omega dot S now 2. All right. So if we consider this, the flux, by the way, sorry, the flux is it's a quantity of the surface integral if the vorticity varies, right? If it's not constant at all points on our surfaces, it's given by the integral over those surfaces against the differential area. Now, what does Kelvin circulation theorem say? Kelvin circulation theorem says that the flux at S1 and the flux at S2 are the same. It says that the integral of vorticity dot ds evaluated on S1 is equal to the vorticity, the flux of vorticity on S2. Or thinking of it differently, the term d by dt of the quantity omega dot ds is equal to 0. And this is true for any vector field with the evolution equation d by dt of omega is del cross u cross omega. So if our evolution equation is d by dt of omega, then we have that the flux of vorticity on any surface in the flow is a constant quantity. We call this we say that the vorticity omega is frozen in. It's the frozen in condition of the flow. In some senses, the vorticity is carried by the flow as the flow changes, and the vorticity can't leave the flow.